So chapter 7 is about the aggregate loss model. So I will break down this chapter into several videos. So the first is about the model. Okay, so here we define the aggregate model as a model like this. So you can see this S is a sum of variables x1 up to xn, and here you can see that the number of x in the summation is random. So this n normally can be interpreted as the number of claims or number of payments. The x are the claim amounts or the payments. So the model is like the compound model we studied in chapter 5. Okay, so here there are some assumptions. For example, when n is 0, then we define s to be 0. The x are IID and they're independent of n. So the main difference between the model here and the compound model we studied in chapter 5 is that the x here might not be discrete. So they can be discrete, they can be continuous. Okay, so now this is the model we want to study in this chapter. So this S represents the aggregate payment. So for example, x1 is the payment from the first accident, x2 is the payment from the second accident, and so on, and there are altogether n accidents, and x capital N is the payment from the last payment, okay, from the last accident. So that's why this S represents the aggregate payment. Okay, so now we are interested in finding the distribution of S. So to do so, we can look at two cases. For example, when the x are discrete, then we are basically studying the same model as in chapter 5. So this is just the standard compound model. In this case, we know that the PGF of the aggregate sum S can be represented as the PGF of n evaluated at the PGF of x. So this is the primary and this is the secondary. When x are continuous, it is more common to use MGF, so moment generating function, instead of PGF. So we can evaluate the MGF of S by definition like this. And then the second step is to use the double expectation formula, so we condition on n. And then to evaluate the inner conditional expectation, okay, so which is conditioned on the variable n, we first condition on the event n equals n. So when n is n, we can replace this capital N by small n. And now, because the x and n are independent, so we can throw away this condition. So it becomes an unconditional expectation. And then finally, because we have assumed that the x are IID, so they are independent, so we can factorize this expectation into product. And then because the x have the same distribution, so these n expectations are identical to each other, and each of them actually is the MGF of x. So that's why this is just the MGF of x raised to power n. Okay, so now we can plug this back to this, and then we can obtain that the MGF of the aggregate payment S is just the expectation of the MGF of x raised to power n. And then because the PGF of n is defined like this, so here u is the dummy variable, and now u is replaced by this mxt. Therefore, the MGF of s is just the PGF of n evaluated at the MGF of x. Okay, so that means if you know the distribution of n and also the distribution of x, we should be able to evaluate this right-hand side, and therefore we should be able to find out the MGF of s. So if we know the MGF of s, then we should be able to find out the distribution of s. Okay, so now we look at moments. Okay, so moments are easier. So in fact, the formula for the mean and the formula for the variance are exactly the same as in chapter 5. So the mean of S, the aggregate sum, is the mean of n times the mean of x. And then the variance formula is similar. So be careful, we have a square to the mean of the secondary. So we square the mean of x. Okay, so the two formulas are exactly the same as in chapter 5. Okay, so basically the aggregate model we study in chapter 7 is very similar to the compound model we study in chapter 5. The only difference is that x here can be continuous. And in the case of continuous x, we use MGF rather than PGF. But the mean and the variance have the same formula. Okay, so now we look at one example. So remember in chapter 6, we consider policy with deductible. So in this case, the per loss variable y superscript L will be x minus d plus. So if x is bigger than d, then the per loss variable is x minus d. Otherwise, it will be 0. The per payment variable is a conditional variable. It depends on x bigger than d. So when there's a real payment, this y superscript p will be defined as the payment. So it is the payment given that there's a payment. And now we define two variables, SL and SP. So SL is just the sum of YL, and SP is the sum of YP. Okay, and here in the first sum, the number of YL to be included is NL, the number of losses. And then here it is the number of payments. So we want to show that the two variables have the same distribution. So how to show this? So to do this, we look at the MGF. Okay, so in order to show that two variables have the same distribution, we need to show that, for example, they have the same MGF. So now we look at the MGF of YL. So by definition, it's like this. Okay, and then YL by definition is x minus d bracket plus. And then we use the total expectation formula. So we condition on whether x is bigger than d or x less than d. Okay, so in the second case, when x is less than d, this positive part function becomes 0. Okay, and in this case, when x is bigger than d, we can drop the positive sign. Okay, and remember in chapter 6, we denote this probability as v. Okay, so now the second expectation is just 1 because e to the power 0 is 1. Okay, and this is 1 minus v, so that's why this whole thing becomes 1 minus v plus v times this. Okay, and now we also look at the MGF of YP. So by definition, YP is the conditional variable. Okay, YP, remember, is x minus d given x bigger than d. So the MGF will be a conditional expectation. So the conditional expectation of exponential t x minus d given the condition x bigger than d. And now you can see that this conditional expectation is exactly the same as the conditional expectation here. Therefore, the MGF of YL equals 1 minus v plus v times the MGF of YP. Okay, so now we have a relationship between the two MGF of YL and YP. And now we can use our formula for the MGF of the compound sum. Okay, so now the MGF of SP by our formula. Okay, so the formula here. The MGF of the aggregate sum is the PGF of n evaluated at the MGF of x. Okay, so we use this formula, apply to SP. Okay, so it will be the PGF of NP evaluated at the MGF of YP. Okay, and in chapter 6, we know that the PGF of NP is related to the PGF of NL through this relationship. Okay, and then we can see that this 1 minus v plus v of the MGF of YP is exactly here, which is the MGF of YL. So we replace this by the MGF of YL. But then by the same formula, this PGF of NL evaluated at the MGF of YL is just the MGF of SL. Therefore, the two variables SP and SL have the same distribution, have the same MGF, and therefore they have the same distribution.